We're going to start our discussion of Chapter 6 with this lesson. And Chapter 6 is all about modeling events, and so looking at probabilities, and we're going to get into something called the normal distribution in the next section. But in this section, we just kind of want to get our feet wet with what we mean by modeling a random event. And the way we model those events is by using something called a probability distribution. So let's write that down. That's actually the name of the section, probability distribution. So a probability distribution gives us a way to look at all the different outcomes or scenarios that are possible with a given random event, and then look at the probabilities that are associated with each of those outcomes. So this line right here says a probability distribution, sometimes we call that a PDF, is a tool, and it can either be a table or a graph, and it tells us those two things. So it tells us each possible outcome, so each event that could occur in that distribution. For example, if I flip a coin, what are my outcomes? It could land on heads or it could land on tails. If I roll a six-sided die, what are my outcomes? It could land on a 1, 2, 3, 4, 5, 6. So each event that is possible, that's going to be your outcomes. And then along with that, it tells you the probability of each outcome occurring. So the probability of each outcome occurring. How likely is it that it's going to land on heads? How likely is it that I'm going to roll a 2? Just some simple examples. But those are the two main things you want to remember for a probability distribution. It tells you what each possible outcome is and the probability of each outcome occurring. So two features for probability distribution, all of the probabilities, and by the way, remember this notation from Chapter 5, so capital P of X, this notation right here, that means the probability. So if X is the event or the outcome, all probabilities of each outcome must be between 0 and 1. And that should make sense based on what we talked about in Chapter 5. Probabilities themselves have to be between 0 and 1, so that rule still applies. Each probability's got to be between 0 and 1, and the sum of all of those probabilities has to equal 1. So whatever the events are, if I'm listing all of the possible outcomes and I'm listing the probabilities for each of those outcomes, if that covers all the outcomes in my scenario, the sum of those probabilities has to add up to 100%, because one of those things has to happen. So let's do a simple example here. It says, consider the random variable x such that x equals the outcome of rolling a die. So we're going to assume it's a six-sided die. Give the probability distribution for this random variable. So a probability distribution very often is a table, and so let's do a table to represent this. So I'm going to do a column to list each outcome, and then a separate column to list each probability. So what are my outcomes for rolling a die? I could roll a 1, a 2, a 3, 4, 5, or a 6. Those are my possible outcomes. And so then what is the probability of each of those outcomes? The probability of rolling a 1 would be 1/6. Probability of rolling a 2 would be 1/6. Probability of rolling a 3 would be 1/6. Rolling a 4 would be 1/6. Sorry, this is a little messy here. Probability of 5 would be 1/6, and the probability of rolling a 6 would also be 1/6. So notice that each of those probabilities is between 0 and 1. They're all 1/6, so they're less than 1. In this case, it happens to be that they're all the same. That's not going to happen every time. That's just because in this example, we're equally likely to roll a 1 through 6. They could all come up, same probability for each event. But do notice that all of these events, if you added these up, they would sum of up to 1. So 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6. All of those add up to 1. So then the question is, what is the probability of rolling a 5 or a 6? Notationally, you may see this listed this way. The probability that x equals a 5, comma, a 6. So either a 5 or a 6. And so since those are mutually exclusive events, we can just add the two probabilities together. So 1/6 plus 1/6 gets us 2/6. And of course that can be reduced, but I'm not going to worry about it. So that's an example of what a probability distribution in a table format would look like. Let's do another example. Consider the random variable x such that x equals the number of stars given by a randomly selected book reviewer. So we've got options to have 1 through 5 stars. It looks like based on the graph, they can't have a half of a star, so it's just 1, 2, 3, 4, or 5 stars. So it says, with some research, the top of the following page, on this page I guess, is an example of what the probability distribution for this graph would look like. So this graph, I've heard it called a spike graph because it looks like kind of the line goes up and then there's a dot at the top where the graph stops at. So along the bottom, you've got your 5 scenarios or your 5 outcomes that are possible here. And then along the vertical axis, you've got your probabilities for each outcome. So like the probability of selecting a book randomly that only has a 1-star review would be somewhere between 0 and 0.1, maybe 0.02 or something along those lines. Notice that all of these probabilities are less than 1, and if we were to add up the heights, probabilities for each of these graphs, we would get a total of 1. So it says estimate the probability that a book reviewer gave a given book a 3-star rating. So notationally we're looking for the probability that x is equal to 3 stars. And so I'm going to go here to my 3 stars column, and then I'm just going to go up and over, and again I'm estimating because I don't have an exact number here. Looks to me like it's approximately maybe 0.11 or maybe 1.12, something like that. So it's about 11% chance that if I select a book, it's going to have a 3-star rating. Okay, let's look at another example. So when a certain type of thumbtack is tossed, the probability that it lands tip up is 80%, and the probability that it lands tip down is 20%. So if U means the tip is up and D means the tip is down, list all of the possible outcomes when 2 thumbtacks are tossed. So we're assuming that they are independent. The way one tack lands theoretically doesn't impact the way the second tack lands. Either we're doing them sequentially or they're not going to intersect with each other when they hit the ground or anything like that. So I think we can assume that yes, they're independent. So let's fill in the probability table. So the probability that both tacks land up. So remember back from the last chapter, the reason they asked about independence is from the last chapter we said that if 2 events were independent and we wanted to calculate an AND scenario, so in this case the probability that the first lands up and the second lands up. What did we do when they were independent? Remember that meant that we multiplied the probabilities together. Okay, so we can multiply the 2 probabilities together to get the probability of the AND scenario occurring. The first lands up and the second. So the probability that they both land up, the probability that the first one lands up from up here is 80%. So it's going to be 0.8 times 0.8. And I'm getting, actually, let me erase this. Let me write this above it so I have a little bit more room here because I want you to see what I'm doing. So this is 0.8 times 0.8, and so that gives me 0.64. The probability that one lands up, or let's say the first lands up and the second lands down. So again, they're independent. So probably the first lands up is 0.8. Now the probability that the second one lands down, remember that had a different probability. That was the complement of the first event. So that would be 0.2. So when I multiply those together, I get 0.16. And then the probability that the first lands down and then the second lands up, it's going to be the same idea. I'm going to do 0.8 for the first one. No, sorry. 0.2 for the first one, that it lands down, times 0.8 for the second one. So I'm getting 0.16. Of course, the order you do those in doesn't matter, but I want you to see that I think if we think about it sequentially, the first lands up, down, the second lands up. And then the last one, the probability that they both land down, so that would be 0.2 times 0.2. And so together, when I multiply those together, I'm going to get 0.04. So a couple of different things to notice here. We've got all of our different outcomes. There were 4 possible outcomes, right? That they could land up, 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 down, down, up, or down, down. Each probability is less than 1. Each probability is like the first one is 0.64, the second one is 0.16, third one is 0.16, the fourth one is 0.04. So they're all between 0 and 1. And here's the thing, get your calculator out and add these four probabilities together. So add the 0.64 plus the 0.16 plus the 0.16 plus the 0.04, and you'll find that you get a sum of 1. And that's what you should get in a probability distribution. All the individual probabilities should add up to 1. So part C says, now we're changing kind of the question a little bit. It says, let X equal the number of thumbtacks that land tip up. So it's a different way of looking at this scenario. This time, X, our outcome, is the number that land up on those two, out of those two tosses. So what are the possibilities? 0, so neither could land up. 1 could land up and the other lands down, or both of them, or 2 could land up. Those are the only three outcomes here. 0, 1, or 2 could land up. So in the first case, the probability that 0 land up, there's only one way that can happen. That's the probability of the down-down scenario in the previous chart. And so that was 0.04. How many ways could they land so that one of them lands up? Well, it could have been the up-down scenario, so the probability of landing up-down, and then the probability of the down-up scenario, probability of landing down-up, and so that would be 0.16 plus 0.16, which of course is 0.32. And then how many ways could they land so that 2 tacks land up? That was only one way that could occur. That was the up-up scenario, and that probability was 0.64. Again, what do you notice about each of these probabilities? They're between 0 and 1. You've got 0.04, 0.32, and 0.64. And then like I said before, if you add those together, you get a sum of 1. So all of the different outcomes, the scenarios, whatever they are, the probabilities should add up to 1. All right, so let's switch gears for a minute and let's talk about different types of numerical variables that we're going to be working with in this section and the next section. So there's two main types of numerical variables. And so far in this course, we've said we have data can either be numerical and categorical, and that doesn't change. That's still true. But for the numerical variables, we're going to break that down a little bit further. And so we're going to say one type of numerical variable is called a discrete variable. I'm going to write that over here too because I think that's hard to read. Discrete. So a discrete variable are numerical variables that you can count or number. Count or number. So discrete would be like the number of, number of posters you have on a wall, or number of pictures on your iPhone. Those are things that you can count. 1, 2, 3, 4, 5. The other type of variable, numerical variable I should say, is continuous. Continuous. And again, I didn't write that very neatly. Let me see if I can write a little neater down here. Continuous. So numerical variables that are continuous, they cannot be counted. Okay, so what do we mean? What kinds of things cannot be counted? They have to occur over a range of values. And generally these would be things like measurements. Think someone's height. Can I count someone's height? Or if let me think of a better way to say that. I can't, if I say what is somebody's height, they could be anywhere from 2 feet tall, well, not 2 feet tall, I guess. They could maybe 4 feet tall to 7 feet tall. And there's an infinite number of heights somebody could have in between those. They could be 5.5 feet tall. They could be 5 3/4 of a foot tall. They could be infinite number of things in between them because it's a measurement. So it's a range of values that somebody could land anywhere in that range. But you can't count the numbers. That's the difference. That's the big difference. So let's do some examples here. Determine if these are discrete or continuous. Number of siblings somebody has. Can you count the number of siblings you have? You can, so that would be discrete. Heights of basketball players. So here we go. Here's your heights example. So heights of basketball players. And I know we're talking about basketball players, but we're talking about the height. The measurement itself is a range of numbers that it could be. So that's going to be continuous. Number of cars owned by a household. You can count the number of cars, so that would be discrete. Number of pets owned by a student, that would be discrete. Heights of buildings in downtown San Francisco. Heights, again, can be any range of numbers. In between, it's a measurement, so that would be continuous. Wait times in a doctor's office, and I just realized wait is spelled wrong. This is like the weight that when you measure something, a weight. I think what they meant, because they said wait times, was how long you're sitting there. So the wait, W-A-I-T, wait times in a doctor's office. And again, times that you're sitting there, time is a measurement. It can be anywhere from 5 minutes to 10 minutes and literally anything in between. So that would be a continuous variable. So then it says, since the values of a continuous, is the blank here, continuous variable cannot be listed, a probability distribution using a table or a spike graph is more useful for a discrete variable. And I want to just quickly go back to the first couple of examples we looked at. These were examples of discrete variables. The number of ways a die could land, 1 through 6, those can be counted. The number of stars somebody could give, we only had options of 1 through 5, those can be counted. So you notice that we used a graph, like a spike graph, and a table for both of those. Same thing with the thumbtacks. We used a table to list all of the different probabilities because those were discrete distributions. There are only so many ways the thumbtacks could land. Continuous distributions, however, that doesn't work. So when we talk about a continuous probability distribution, another name for it is called a density curve, or the graph of it is called a density curve, also known as a probability density function. These graphs have an area. That's this word right here. I didn't leave you much room. Let me write that below here. An area under the curve that must equal 1. So the area under the distribution or under the curve, that's considered the density, those areas represent probabilities. So the area under the curve represents the given probability for different events. And we're always going to look at continuous distributions in terms of a range of numbers. So let's do an example. The probability density curve shows the probability of wait times before service at a coffee shop. So again, wait times, that's a measurement. There's a range of numbers. I could be waiting anywhere from 0 to whatever minutes and anything in between. So that means this is a continuous distribution. So keep hammering that in your mind. Is this continuous or is this discrete? Because that's a really important distinction. The shaded area below represents the probability of wait times between 0 and 2 minutes. So they're talking about this pink area right in here. The total area under the curve is 1. Now, even if they didn't tell you that, you should know the total area under the entire curve has to represent all of the possible areas we could have for that distribution. So it's got to add up to 100%. So the area under the curve, the entire area, has to add up to 100%. The question says, what is the minimum time to be waiting at the coffee shop? So based on that x-axis, it looks like 0 is the minimum time we could be waiting. And the maximum time, I think our probability stops right about here. Doesn't look like we have any area underneath any numbers past 5. So I'd say 5 is the maximum time. So based on the graph, approximately what is the probability that somebody will be waiting between 0 and 2 minutes? So they're asking you to figure out an estimate for what's in the pink area. Okay, so remember, the entire curve, so from 0 to 5 minutes in this example, the entire curve has an area of 1. So if I were to shade in all of this all the way to the 5, so from 0 all the way to 5 and fill all that in, that entire area would equal 1. And that would be the case, even though if they didn't tell me that would always be the case for a probability density function. They want me to figure out an estimate for what I think is the pink area because that's 0 to 2 minutes. I'm ballparking it. I don't know what the actual area is because it's kind of a strange shaped figure. So I'm ballparking it and I would estimate that it's about half of the entire area. And so if it's about half of the entire area, that would be 0.5, or if we write that as a percentage, 50%. So it's going to be about a 50% chance we're waiting between 0 and 2 minutes. Let's look at another example. So finding probabilities for, these are called uniform, continuous, I'm going to abbreviate and say continuous distributions. So a uniform distribution is where the probabilities of all of the events have an equally likely chance of occurring. And you can tell in this figure, we're looking at times at a bus stop. So let's read the example. A bus arrives at a certain stop every 12 minutes. The graph below shows the probability distribution for the continuous random variable x, and x represents the wait time before the bus arrives. This is an example of a uniform distribution, or a distribution in which every possibility for the random variable is equally likely. So what we mean by that is we can be waiting anywhere from 0 to 12 minutes. And the probability of waiting 0 minutes is the same as the probability of waiting 12 minutes, is the same as the probability of waiting 5 minutes, 10 minutes, anything in between. How do I know they're all the same? Because I'm looking at the height of that curve, and they all go up to about 0.083. So at any individual time, it's about an 8% chance of me waiting that long at the bus stop. So the question says, and that's what we mean by a uniform distribution. Use this distribution to find the probability of a wait time that's between 4 and 10 minutes. So how am I going to figure this out? All right, so I'm looking for area because it's a continuous distribution, and I want to know the probability of waiting any time between 4 and 10 minutes. So I'm going to mark where I think 4 is, and of course 10 is already marked. So what I'm looking for is the area underneath that curve from 4 to 10 minutes. So this rectangle that I'm shading in represents the area under the curve. The area in this rectangle represents the probability that I'm going to be waiting between 4 and 10 minutes. So below that, the blank there, it says we need to find the area of the rectangle. And that's how you're going to handle it if you have a continuous distribution like this. You're looking for the area from point A to point B, whatever they ask. The computed value of this area will represent the probability of a wait time between 4 and 10 minutes. The picture below this has this information already in it. So there's the same thing, but they've gone ahead and shown you the rectangle in red. So to get the area, because it's a rectangle, and we do know the formula for the area of a rectangle, it's not a weird shape like we had in the last example, we're going to compute the length by the width. So the length this way would be 6 minutes, right? Just 10 minus 4. And then the width, or the height if you like, would be the number we had up here. It doesn't show it on this graph, but from the previous graph we know it was 0.0833. And it was 33 repeating, so I'm going to put that in my calculator. I get approximately 0.499 something repeating. So again, about 50% chance. We're going to be waiting between 4 and 10 minutes. One last example here. Suppose an instructor designs lessons so that the class lengths are uniformly distributed between 72 and 77 minutes. That is, any time between 72 and 77 minutes is possible, and all the possible values are equally likely. So here's a graph of it again. So we're going from 72 to 77 minutes, and they all have a chance of occurring. Any individual time has a chance of about 20% of occurring. So it says if we let x be the random variable representing the length of that class, then the random variable x has a distribution that can be graphed below. So part A, is the length of the class continuous or discrete? We're talking about times. Times are a measurement, and they can take on any range of values, so this would be continuous. Can a probability distribution table be created for this random variable? So table, no. Why not? Because it's a continuous distribution, so we have to use a graph instead. The probability density curve for the random variable is given below. What is the total area? Remember, the total area represents all the possible areas, all the possible scenarios that it could occur. So the total area, the class has to be between 72 and 77 minutes. And there is a 100% chance that it's going to be between 72 and 77 minutes. So the area under that curve has to be 1. That represents a 100% chance that we're going to be between 72 and 77. Part D says determine the probability the class runs over 75.5 minutes. I really recommend that you put this in your picture and you label where you think 75.5 is, because we're looking for the area under the curve that is over 75 and 75.5. So it's going to be greater than the 75.5. The biggest it can be is 77. So the region that we're talking about is right in here. So the area we're looking for, area under the curve, we're going to use the formula for the area of a rectangle again. And so let's see, the area is going to be, the width would be, let me write it up in here because I'm short on space. The width would be 77 minus 75.5. 75.5 times the height. So the height, of course, is this number right up here. That's how tall we are on the y-axis. That's 0.20. So that's 1.5 times 0.20 or 0.2, and I'm getting about 0.30. So there is a 30% chance, remember that's a percentage, there's a 30% chance that class will run over 75.5 minutes.